components of Hodge loci of minimal codimension. Okay.
Hello. For me, it's a great pleasure to be here. Thank you very much for the invitation. Today I will talking about the component of Hodge loci of minimal codimension. This is what I worked on with Roberto Villaflor. In some moment of the talk, I will repeat that Roberto explained in the morning. So I think it's not so bad to do that. So the overview is this. In the first two parts, I will give a little historical tour. In the last part, I stated the main theorem that complete the last theorem that Roberto stated in his talk. I will give the main idea and the main ingredients behind of the theorem, of the main theorem. So we define the Noether-Lefschetz locus as the set of a smooth surface of degree D, so that its Picard number is greater than 1. And it's a classical result stated by Noether proof of Lefschetz say that a general smooth degree D surface has a Picard number equal to 1. Doesn't mean that the Noether-Lefschetz locus is the union of a countable of Zariski closed sets. So in the development of, I don't know how to say, in the development of infinitesimal variational of Hodge structure given by Carson, Griffiths, Green, and Harris, they delivered a tool to study the different components of the Noether-Lefschetz locus. In fact, in this work, they ask what is the smallest possible codimension of the components, if can we characterize them. This question in this context was solved by Wassani and Green independently. They found that the small possible codimension is D-3, is only attained by the surface shows that contain a line. For this theorem, we know that the codimensional of the components of the Noether-Lefschetz is between these two numbers, between D-3, between these I don't know how to say that, D-y taking 3. Also, just for more complete history, was unproved proof that the next small codimension is 2D minus 7. And it characterizes that. This is only attained by the all surfaces that contain a conic. So now I will define the analogous in higher dimensional hypersurface to the Noether-Lefschetz. That is this the Hodge locus. Sorry. Yeah. Because in D equal to 4, all the components are the same codimension. So, okay. Consider the family of smooth hypersurface of degree D in dimension n even. It takes a Hodge cycle, so that is not trivial. For me, not trivial means that the primitive part is different from 0. So with this we can define the local Hodge locus. There are parameters of that way where you deform is this Hodge locus. Sorry, is this Hodge locus by I don't know the flat deformation or the locus remain, the cycle, the hot cycle remains hot. So if you use a Poincaré duality, you can describe this set as a family of holomorphic functions, so that are vanishing. So this means this set is a analytic variety. In fact, they has a analytic structure, or how to say that? Wait. This has a analytic. Sorry, I don't know how to say that. This is an analytic scheme that has a structural analytic scheme. On the other hand, we can define the hot locus. They are, okay, we can define the hot locus. They are all hypersurfaces so that they contain at least a no primitive hot cycle. And in this context, when you put n equal to n equal to 2, by 1-1-Lefschetz theorem, the hot locus is equal to the Noether-Lefschetz locus. The fact is that there are a relation between the hot locus and the local hot locus. The relation is the following. Carson, Green, Griffiths, and Harris proved that the hot locus is a countable union of properly analytic subvarieties. Also, every irreducible component is equal to some local hot locus associated to a hot locus, associated to a hot cycle. The fact is, if the hot conjecture is true, you have the hot locus is a countable union of Zariski closed sets. But in fact, Cattani, Deligne and Kaplan proved this independently of the hot conjecture. So it's natural we do ask the same question about what is the smallest possible codimension of the whole locus. Can we characterize them? So a partial answer was given by Movasati or Tinoska is the following. If you consider the big enough, or if the component contains the Fermat variety, the smallest codimension is this number. In fact, if you put here n equal to 2, you obtain d minus 3. That was the previous number or the number, the smallest minimal codimension in the case of the Noether-Lefschetz locus. If for the big enough is only attained by the space of hypersurface such that contain a linear subvariety of dimension n over 2. It's similar to the case of Noether-Lefschetz locus. Okay, I don't know. Okay, with this theorem, in this context, we have the codimension of the component of the hot locus are between these two numbers. This number here, this. In fact, you can obtain this unpaired bonder using the definition, and also I think this the Griffiths transversality. The point is that all these results led to Movasati to conjecture the following. Assume that you take a hot cycle in the Fermat variety. You assume that the Zariski tangent space associated to the hot locus. Assume that the Zariski tangent space to the hot locus, to the local hot locus associated to this this cycle is the minimal codimension. Then Movasati said that this cycle is in fact a linear cycle. That means that the minimal codimension of its host local host locus determines the cycle. Furthermore, the smallest codimensional component contained in Fermat is precisely the all hypersurfaces that contain a linear subvariety. The things is that, as Roberto said, that was true. Roberto proved in a previous work that was true for the different 3, 4, and 6. So in the work that we did, we prove. I don't know how to not prove. We tried this other case. And the point is that the first part of this conjecture for this case is false. It's not true. But despite that, the second part of this conjecture is true for all the always that you stay around the Fermat variety. All this is around the Fermat variety. More precisely, the Movasati conjecture fails, but more precisely, there are infinitely many different host loci associated to a not trivial host cycle, so that the codimension of the Zariski tangent space of this local host locus is the minimal codimension. In particular, there are infinitely of these host cycles are not linear. We call them fake linear cycles. In fact, we describe the fake linear cycles completely in terms of via the Griffiths basis. So I don't know. Okay, fun curiosities in this case, the group of algebraic cycles are their rank is is the maximal rank. Yes. That means that in this case the host conjecture is true. In this case, in the Fermat variety for degree 3, 4, and 6. In fact, the space of hot cycle is generated for linear cycles. So I told some of the ideas behind this theorem. So we have the Griffith basis. For this, we consider this Jacobian idea the Jacobian ring. The Griffith basis describe the class, the cohomology class in terms of the Jacobian ring. In fact, we can identify the mirror of the cohomology with this part of the Jacobian ring. This identification is via the residual map. In fact, it's compatible with the host decomposition. Roberto explained that. This is the I don't know, classical top form. On the other hand, we can define, we can consider a hot cycle not trivial. We can define the Artin-Gorestan ideal. Is the quotient of these two ideal, the Jacobian ideal with the ideal generated by the polynomial given by the Griffith basis. So why this Artin-Gorestan idea is important? We have the two local host locus are the same, and only if the Artin-Gorestan idea is the same. Is in only if the primitive the primitive class that they induce are the same. They say that the two hot cycles are the same in primitive class, except by a constant. So this a kind of the describe algebraically the geometric information that we have in the local hot locus. Other important property is that the Artin-Gorestan ideal give me the first order approximation of the local hot locus. That's we need. Okay. Okay. The first part of the proof is try to characterize the polynomial associated to the hot cycle lambda. So for this, if we have the codimensional of the Zariski tangent Spain is minimal, as Roberto explained, we obtain the polynomial has this exact form, where these constants are in the complex number. Different are not zero. So the second, okay, but we have this relation just for remember the primitive class of the hot cycle is given by. We have a unique correspondence between P lambda and the cycle lambda via Griffith basis. The next step is to bond the field of definition of these constants. How we do that? Okay, how we do that? Remember I don't know. Remember that we have the. Okay, we have the. The RAM homology via the is generated by via the Griffith basis is generated by this omega beta. With this omega beta is the residue de x0 beta 0 xis 1 beta 1 blah 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 xis n más beta n plus 1. Okay, aquí there is some constant. This k depends on where part the omega beta in the host decomposition there is the omega beta. That means that this kind of differential form are a basis of the homology, the rank homology. But we can also take a basis of homology group of this variety. This basis is called, I don't know how to say, vanishing cycle, I think, vanishing cycle. So if Deligne gives up a period formula in I don't know how to say, they relate the omega beta, this omega beta, with the vanishing cycle. The point is that if the hot cycle in particular is a rational class, that means that some periods are rational number. So we use that for obtain that the constant C lambda is in this field. If the order constant is in this set, where this notation is the element in this field, so that the norm is equal to 1. So until now we bounded the field of definition of the constant. So just for remember, the polynomial has this form, and with the constant are in this set. Maybe I am wrong here. Okay. with this description, we know the Hodge cycle is described as a sum of omega beta. Remember, the omega beta is a basis. But this omega beta satisfies this arithmetical condition. The beta 0, beta 1 is equal to d minus 1, beta 2, beta 3 is equal to d minus 2 is, go ahead. So before to go the next step, let me, I describe the spectral decomposition of the rank homology at the Fermat variety. That is given by the action on a commutative group in the Fermat variety. For this, we consider the Fermat variety, consider this finite commutative group given by the group of the roots of unity. This group acts in the Fermat variety by coordinate ways multiplication. And the character group of the dual group of this group is the character group that is defined in this way. So, this is the action, the character group in the group. So we have this group has an action in the Fermat variety. This action descends of the cohomology of the singular cohomology. You can extend this action to all the RAM cohomology. This action induces a decomposition in the RAM cohomology. This decomposition is finer than the Hodge decomposition, but this is finer. But this decomposition is compatible with the Hodge decomposition. In fact, okay, B the lambda is this kind of eigenspace given by the character. In fact, Schrödinger proved that all these spaces B alpha are unidimensional or zero. He describes how is the Hodge decomposition in terms of the B alpha space. In the last one, this describes how are the space of Hodge cycle with coefficient in the complex with this arithmetical condition. In fact, if you combine this theorem with the Griffith-Basis theorem, you have that B alpha is generate what C with omega beta. What is the relation with the character alpha and beta? So you have the beta jota is equal to a jota minus 1. This is the relation. Okay, so we define the for every cohomological class in the RAM cohomology, the field of definition of this form. How we define that? You put the all periods of this form. You add the. It means you consider this extension field with the all periods of omega. Since this homological group is finally generated, this field of definition is also finally generated. And this is the field of definition in the sense that the form, the differential form, belongs to this singular cohomology group with coefficient in this field. After that, we define the Galois action, for every element in the Galois group, we define the Galois action in cohomology in this way. We say that the Galois action satisfies this equality. When you do the Galois action in the differential form, after that you do the periods. That is the same that you do the periods in after that do the Galois action. Okay. Okay. The next step is show that the definition field of this omega beta is contained in this cyclotomic field. After that, characterize the Galois action in omega beta. Remember okay, no matter. This is for every omega beta. But is this we will characterize the action the Galois action not for all omega beta, only for omega beta that satisfies this condition. This condition here. This condition. Because we are thinking in this hot cycle. So, okay. So it's very easy to see that we know that B alpha is generated by omega beta, but now consider this differential form. Is omega beta with this constant. This constant is so in some way that when you compute the periods of the where is that? When you compute the periods here, when they use the period formula with the eta alpha, you obtain that these all periods are in a cyclotomic field. That means that the differential form eta alpha belongs to this singular cohomology with coefficient in this field. It's just a normalization. The point is this happens. We have we can check by simpler property of gamma function that this constant is in this field. That means that well, okay. We also have by the previous theorem, by how we define the Galois action, that the action in this form is in this way. It's just do the action in the parameter alpha, in the character alpha. That means that the field of definition omega beta is contained in this cyclotomic field. Okay. Okay. Now we need to describe how to describe the Galois action in this omega beta. How we do that? We know if I take a algebraic cycle, the Galois action, I don't know how to say that cycle. Okay. If I took algebraic cycle, this cycle is invariant by the Galois action because it is a rational class. So I need looking for algebraic cycle so that in this sum this kind of omega beta appears, but the The Fermat variety, we know a lot of algebraic cycles, especially the more simple. If you take a linear algebraic cycle, you can check you can write this algebraic cycle as a sum of this omega beta with decent condition. The differential between this and this are the constants. So using this, we have a bunch of identities. With these identities, we can conclude that okay, this is what I say. With this identity, we can conclude that how is the Galois action in omega beta. So we know how is the Galois action in omega beta. So we can apply the Galois action in this cycle, because we know this cycle is in the middle of the pair, but we don't know if this cycle is already is the fact a hot cycle. Okay, so the next step is prove that for any election of C0, C2, in this, there exists a C lambda so that the cycle is in fact a hot cycle. That means that the field of definition of the cycle lambda is the rational number. But this is equivalent to prove that the cycle is invariant for the Galois action. But we know how to act the Galois action in this cycle. So this cycle is invariant in only if you have this bunch of identities. This phi is a complex number. You can take this phi as a function, so that for every t in the Galois group, this gives you a complex number. But think only in this question. By definition, it's a compoundary in this cohomology group. But we have the Hilbert's theorem 19 that say that this group always is trivial. So we need proof that this phi de t satisfies the one cocyclic condition for how to say that? Wait, if we prove that phi de t is a one cocycle, we can use the Hilbert's theorem if we know that this cocycle is really a coboundary. That means that exists C lambda. The point is for degree D3, 4, in 6, we can check that this phi de t is one cocycle, because we can compute this phi concretely for degree 3, 4, in 6. Let me say that with these same ideas, we can prove that the other D's, these C0, C2, Cn, are the fact I don't know how to say that they satisfy this. That means that the cycle associated to this this means that where is the wait? That means that the cycle associated to this polynomial here is in fact a true linear cycle for the other D's. That means that with techniques we can do another proof that the Roberto's theorem. Okay. But we also as I say, we also proved that even anomalous hot cycle, we can prove that the unique component of minimal codimension of the hot locus passing through the Fermat variety is the one parametricized per surface contain linear subvarieties, as the same in the case of Noether-Lefschetz locus. How we prove that? For this, I need to talk about the quadrangular fundamental form. So for this, we consider a smooth m-dimensional analytic scheme and consider a vector bundle on M. Also consider a W as a zero locus of a section sigma of B. The definition of the quadrangular form is defining the Zariski tangent space in a point, in a x point, in a point in this W. Is defining this in these local coordinates by this formula. This quadrangular fundamental form is like a second order approximation of the local hot locus. The important thing about this is if the W is smooth, irreduced, that implies the fundamental quadrangular form is vanishing. This is the important fact. The point is, in our context, remember that we have the family of smooth per surface of degree D in dimension n. In our context, we have the M is the parameter, is the space, is the parameter space T around the Fermat variety. If 0 is or x is equal to 0, it corresponds to the Fermat variety. And V is this direct sum of the I don't know how to say that, is the bundle of the hot filtration. If sigma corresponds is a section correspond to hot cycle lambda when you extend locally lambda with parallel transport. And W is the local hot locus. Of course, the tangent space is this part of the Artin-Gorestan idea associated to the hot cycle lambda. If we can identify the fiber with this part of the Jacobian ring. And we can identify the derivative of sigma as a multiplication by the polynomial associated to the hot cycle lambda. The point is that the Maclaurin proof give a explicit description how to compute the quadratic fundamental form. This description is the following. In our context, that you can compute this quadratic fundamental form in this way, with this formula, where this polynomial QA satisfies this condition. This is that because when you multiply G by P lambda, this belongs to the Jacobian ideal. So we have the explicit formula. We can compute the quadratic fundamental form in our context. If we do that, when we compute the second fundamental form with this polynomial, we obtain that is different of 0. That means the local hot locus associated to a fake linear cycle is not smooth or not reduced. With this, we can, in particular, the quadratic fundamental form on a fake linear cycle is not 0. With this, we can prove the second part of the theorem is that We know the affilinear cycle in the Zariski tangent space of its local host locus, the minimal codimension. We need to prove that okay, we need to prove that it's not possible that this codimension is equal to this. But you can assume that they're equal. But there we can, if we have the equality, that means that this local host locus is smooth. If it's smooth, the quadratic fundamental form is 0. But we prove that it's not 0. Okay, this is the reference. Thank you very much.